Hello, this is Mr. Henry, and welcome to lesson 6.1. Describe and construct scatterplots. So we're starting a new module, new unit on scatterplots. The essential questions asks, how do I describe and construct scatterplots? So down here for a warm-up, it's a Collins Type 1 writing, so you'll have 2 minutes, and it asks to list 5 things you know or think you know about scatterplots. So go ahead, pause the video, take your 2 minutes, list 5 things you know or you think you know about scatterplots. When you're ready to continue, hit play, and we'll go through it together. Okay, so hopefully you did this. And since this is kind of an opinion question, I mean, everybody's going to have their own things they might know about scatterplots. You might say, you know that it kind of just looks like a bunch of dots, however those dots look. I mean, yeah, that's kind of what a scatterplot looks like. That would be a scatterplot. Maybe you're more advanced and you know about things of like line of best fit and different types of correlations and bivariate data and all the other kind of stuff that we will be talking about in this module. So let's check out the vocab. We've got 3 vocab words. First one is, well, scatterplot. Like, what is a scatterplot? So a scatterplot is a way of displaying bivariate data when both variables are numerical. And bivariate means 2 different variables. So it's a way to compare things with 2 different variables, with 2 different measurements. We can talk about height and temperature would be 2 different variables that you could use a scatterplot to see if there's a relationship between the height and the temperature. All right. Correlation. This is a big guy for this module. Correlation describes the relationship between those 2 variables. So the possible correlations are, you could have a positive correlation or a negative correlation, strong correlation, weak correlation, linear, nonlinear, or not a correlation, no correlation at all. And finally, line of best fit. When there's a correlation present, we can represent that relationship by sometimes a line. So it's a line that attempts to model the data represented in the scatterplot. So if a bunch of your data fits in a line, so like scatterplot I had a second ago, but something like this, those data appear to follow in a straight line, and so a line of best fit would kind of follow the data, something like that. That's what we're talking about. This line of best fit is a line that attempts to model where the data is. Obviously, the line wouldn't look good if it was like this, because that doesn't go the same direction as the data, or even worse, like that. So it's a line that attempts to go in the middle of the data, looks like the rest of the data, fits the data. So the first thing we're going to do here in these couple of lessons is we are going to just describe some scatterplots. So out of all those different types of correlations, the different types of labels we could give, these adjectives for the type of scatterplot, all of these guys down here, we want to know what is present in the graphs that we have. So let's look at this. So this little scatterplot here, well, a couple things. First off, let's go through the checklist. Positive or negative. So this goes back to slope. So if you imagine these data following a straight line, the line would look something like this, relatively speaking. So would the slope of this line be positive or negative? It should be positive. This line is going uphill. So this line is positive. This correlation is positive. Okay? Next we have, is it strong or weak? Now, strong and weak are kind of, it's an opinion question. So this would be considered a fairly strong correlation because most of the dots, most of the data points, are pretty close to the line. If we would kind of circle this up, I call it like wrapping it in a burrito. If we would wrap this up in a burrito, it's a very tight, skinny burrito. And the tighter, the skinnier the burrito, I mean, if you could get these points to be exactly in a straight line, that would be called a perfect correlation. these points, the way we have them, are pretty good. So this would be a strong correlation. Let's see. Next we have, is it linear or nonlinear? So that's asking, do these points follow a straight line or are they kind of curvy? Well, this appears to follow a straight line, so I would call this linear. And if it is any of these things, positive, negative, strong, weak, linear, nonlinear, then it's definitely not going to be no correlation. No correlation is if there is no relationship between the two variables. So in the example here, we are talking about height and pant size. Because there is a correlation, because this is a strong, positive, linear correlation, we can say that this data, that there is a connection, a relationship between your height and the size of your pants. So as your height gets bigger, so do your pants. Obviously, you're not going to be wearing pants the same size when you're 2 years old as when you're 20 years old. So there is a relationship, a correlation between your height and pant size. And that's what this data would be showing. Okay. Second example here, we're talking about the money spent. So this is more further you go to the right, you're spending more money. And the y-axis is money in savings account. All right. So looking at this data, if I would kind of wrap it up in a little burrito, it's kind of going downhill. I mean, it's a burrito that's kind of like, it's oval shaped, and it's going down like this. So this is a negative correlation. Now, if we compare this and this, look how skinny this burrito is in letter A. This correlation, all the data is pretty close together in letter A. That's why this one was strong. This one, it's more spread out. So this one would definitely be considered weaker than part A. Now, as far as if you call it a strong correlation or a weak correlation, that's kind of an opinion, because maybe you think, well, these guys are still fairly close to the line. They're not really spaced out. I mean, you're not having like points out here and out here. So, but in this case, I mean, relatively speaking, this would be a relatively weak correlation. So I'm just going to put weak. Okay. And then, is this linear or nonlinear? Is it going in a straight line, or does it appear to be in a curvy line? And this appears to be in a straight line. So this is a linear correlation as well. So we could call this data, the relationship between these two variables, a negative, weak, linear correlation. It's negative because it's going down. It's weak because it's not super tight on the line of best fit. And it's linear because they appear to be going in a fairly straight line, even though that's kind of ziggy-zaggy. You would not want to think of it like this and like try to connect all your dots. That's not right. Your line of best fit tries to fit the middle of the data, tries to mimic what the data is doing. Letter C. So here we have a scatter plot that's comparing time and temperature. So let's see. If I kind of wrap this up now, this does not appear to be a linear correlation. I mean, this doesn't seem to fit a straight line. I mean, these data points are all pretty, tightly packed together. I mean, if I had to connect them, I would say the line would look something like that. So I'm going to go right ahead and say this is a non-linear correlation. I mean, as the time goes up, think about early in the morning. Time goes up, sun comes up, temperature's rising, temperature's going up, 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 and then around like 3 o'clock in the afternoon, whatever, then the temperature starts dropping down again. This is non-linear. The temperature doesn't just keep going up and up and up and up and up forever. or down, 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 down forever. It goes up and down. So this would be a non-linear correlation. Now, we could still probably put a label on how strong or weak we feel this is. So this, to me, appears to be a fairly strong correlation. I mean, these points are all, they're not scattered around. There's no large amounts of variance change in the amount of where the scatter plots are. So I would call this a strong non-linear correlation. So there is still a relationship between time and temperature, obviously. I mean, if you look at from day to day to day to day, the same time of the day is usually maybe a high point in temperature, and sometimes it's a low point in temperature. Like 7 o'clock, 6 o'clock in the morning, right before the sun comes up. That's usually one of the coldest parts of the day. Usually. Not always. But the data would show that if you would take all of these points and you would record data for hundreds and thousands and millions of days, it would still follow a same basic pattern where the temperature over time would go up throughout the day and then down after midday sometime. Okay, letter D. Here we're comparing a person's age and the hours of TV they watch. All right, so let's see. If I kind of wrap this up in a burrito, that doesn't look like a burrito. That's more like a waffle. It's square shaped. There's no circle, there's no oval that can be made out of this. So this has no correlation. It's not linear, it's not non-linear. This is nothing. This is no correlation. There's no connection between, according to this data at least, between your age and the amount of TV you watch. So this person's really young, they watch a little bit of TV. This person is really young, they watch a lot of TV. This person's old, they watch a little. This person's old, they watch a lot. And everything in between, there doesn't seem to be, according to this data, a connection between a person's age and the hours of TV they watch. All right, so you start to get a feel for this correlation. You're looking for a pattern in the data based off your data points. Does it sort of form a straight line? If it is a straight line, you're looking for, is it positive, negative? Is it strong or weak? If it doesn't form a straight line, well, that could mean, like this case, it seems to still follow a pattern, so that makes it nonlinear. And because the points are all pretty close together, this would be a strong nonlinear correlation. And if it doesn't follow a pattern at all, if there seems to be no line, no anything that you could draw, nothing that you could find kind of mimics the data, then it would have no correlation. Couple more here. Let's see. So this is comparing your grade on a test and the time taking a test. Okay, so let's see. Well, there definitely seems to be a line. I mean, if I connect this with an oval like this, there definitely seems to be a line of best fit here. Okay, so this is kind of, it's linear, but this is kind of tricky. Believe it or not, this is going to be no correlation. There's actually no relationship, according to this data right here, between the grade you get on a test and the time taking the test. You go, why is that? I mean, there seems to be a straight line. So let's see. So this person got a low grade. They took that much time. This person got a high grade. They took that much time. So these two people took the same amount of time taking the test, but their grades are very, very different. This person took a little bit more time, low grade. This person took the same amount of time, high grade. This person, right over here, got a medium grade with less time, higher grade with less time. So there isn't a variance in mean, everybody took the test in roughly the same amount of time. I mean, I don't know what the units are here, but we could say maybe it's 5, 10, 15, within 20 minutes of each other. So within these 20 minutes, I mean, think of a class period. Everybody has to take the test or the quiz within the same amount of time, and there's going to be varying ability levels. So even though this is linear, whenever you have a graph that is not positive or negative, that would actually be a case of no correlation. So a zero correlation, which is what this line has a slope of 0, zero correlation is no correlation. There is no connection between these variables. So according to this data, there's no relation between your grade on the test and how long it takes you to take the test. All right, next one here. So let's see. This appears to be linear. If we wrap this up in a burrito here, I've got a nice oval shape. And if I split it down the middle, that would be roughly my line of best fit. So this is linear. Let's see. Is this strong or weak? Well, compared to some of the other linear ones we saw, this linear, strong. This linear, we said was weak. This one is about the same. I would call this relatively weak. What are we missing? Oh, is it positive or negative? We didn't say that. Well, this line, since it's going up, 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 is positive. So this would be a positive, weak, linear correlation. All three of these words, these adjectives, describe the correlation and tell you something about it. Because it's positive, that means the bigger this variable gets, the bigger that variable gets. So the more hours you work, the more emails you're getting. That makes sense. It's weak. The weakness or strongness of the variable shows how true this is for everybody. So some people, maybe this person, worked not many hours and got a low amount of emails. This person worked more hours but still got a low amount of emails. So the more change, it just shows how true the relationship is. So this is weaker. So that means this relationship is not as true for everybody. Whereas over here, as your height gets taller, your pant size gets bigger, that's for the most part true for everybody. And linear is the type of correlation because it's fitting in a straight line. Okay, we've got two here for you to try. So this first one is comparing months pregnant and weight gained, and there's your scatter plot. And letter H is the volume inside of a can and the pressure inside of the can. So I'd like you to pause the video, do the problems right now, describe them. What adjectives can you put to those correlations? When you're ready to continue, hit play, and we'll go through it together. All right, so let's see. So if you fit a line to this data is definitely not linear. It's something like that. So this is non-linear. So when it's non-linear, we can't really say if it's positive or negative, because non-linear can be, if I had a bunch of data that was fitting like this, well, in some places it's positive, some places it's negative. So this non-linearness, you can't really say if it's positive or negative. Generally speaking, this one's always going up, 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 up. But we can describe the strength of it. Does this data appear to fit this line very well, or is it kind of weak? Are the points more spaced out away from this central line? And this appears to be a very strong non-linear correlation. It's strong because you don't see a lot of variance. You don't see some points out here that are more spaced out. So this amount of weight gain, based on the months pregnant you are, is a pretty strong relationship. As you become further in the pregnancy, you continue to gain more weight as the child is growing bigger. That's true for nearly everybody. So there's a strong correlation between those two variables. Letter H. Here we're comparing the volume inside of a can and the pressure inside of a can. So let's see. Let's see if I can burrito this thing. That is a very strong correlation. I'm even going to put very strong, because that is extremely tight, compact together. If I could draw my line, I'm going to use actually the line tool to make it perfect here. Those points are almost all in a perfectly straight line. There is a definite relationship between the volume and pressure. So I'm going to say this is definitely linear, and we didn't say if this is positive or negative. This line is going down, meaning the more volume in a can, if you increase the volume, the pressure inside of that can decreases. The pressure is going down as the volume is going up. So this is a negative, very strong linear correlation. All three of those words describe the relationship between those variables. Negative because as one variable is going up, the other variable is going down. As volume is increasing, the pressure is decreasing. Strong because they fit this line perfectly, and linear because the data fits a straight line. Okay, so we've talked about describing scatter plots, and honestly, that's kind of a good bit of what you're going to have to do. You're going to have to be able to describe scatter plots based off a data we get. Okay. Oh, here's one more. So this is a scatter plot that has the numbers of fingers on your left hand and your IQ score. So go ahead and quickly check out and do this problem. When you're ready to continue, hit play. We'll go through it together. All right, so this definitely, again, fits a straight line. This line is vertical. And you might be thinking, whoa, what's the relationship here? I mean, it appears to be linear. It appears to be sort of strong. But is it positive or is it negative? I mean, a straight up and down line is not positive or negative. Remember, positive lines are slanty like this. Negative lines are slanty like this. This is kind of neither. My line in the middle here is not great. Like that. This is kind of neither. This is not very strong. It's not very weak. It's a vertical line, and that has no slope. So this also has no slope. There's no correlation. Even though it appears to be a straight line and appears to be strong, this is kind of like this example, where it wasn't going up, it's not going down, which means there is no correlation between these things. The zero correlation here, or in this case, there's no slope. Vertical lines have no slope. The slope is undefined. There is no slope, so there is no correlation. No correlation. And if you even looked at the variables, the number of fingers on left hand and IQ score, do you think there's actually a relationship between the number of fingers somebody has and their IQ score? I mean, if somebody had a finger chopped off and they have 4 fingers, does that make them smarter, dumber? If somebody's born with a 6th finger, does that does that help their IQ score or hurt their IQ score? No. So it would make sense that there is no real correlation between the number of fingers on your left hand and your IQ score. And that's shown by this data. All right, so we've done this describing. Now we're going to be moving into the constructing. So example 2a here says, the table below shows the results of a study comparing the age of a car in years and the number of miles the car has driven. Graph the data in the space below. Draw the line of best fit for the data. All right, so we have some data, and down here I have a little graph space. So to construct our scatter plot, we're going to take these data points and we're going to plot them. So when a car was 2 years old, it had 15,000 miles. So let's see, the scale seems to be 10,000, 20, 30, 40, 50, 60, 70, 80, 90. So 15 would be here. 566. 566. And if you know what you're doing, you can definitely skip past this part where I'm just plotting it, or do it on your own, work faster than me. 320, 320, 17, 17, 880, 880, 440, 440, 325, 325, 590. That person drove a lot. 655, 655 would be here. 222 and 775. All right, so roughly speaking, that would be the data that we have here. Okay, and so what it asked us to do? It asked us to graph the data in the space below, draw the line of best fit for the data. All right, so you probably gathered this when we did this before, when we did the problems above. But the line of best fit attempts to go through the middle of the data. So I like the idea of lightly sketching in that burrito. So I'm going to turn this down a little bit. So if I lightly sketch, and then my line of best fit would kind of go right. Ooh, didn't mean to tap that. Would kind of go right in the middle of that burrito. Now you're probably thinking, why didn't I include this point right here? That point right there, to me, would be called an outlier. An outlier is a data point that is outside the normal range of the rest of the data. I mean, if that point wasn't there, if you kind of ignored him completely, move him off to the side, don't all those points fit pretty nice and neatly to that straight line? But that one point, what was it, right there, he doesn't fit. And if I would draw my line of best, if I would extend this oval out there, it would make my burrito look not linear anymore. It'd be kind of very odd shaped. So that point is an outlier. Something else to consider when you're drawing your line of best fit is you should have roughly the same number of points above your line as below the line. Now, I didn't count them when I drew my line in here. So let's see here. This one's on. I've got like 1, 2, 3, 4 above, 1, 2, 3, 4, 5 below. That guy is right on. So, I mean, roughly speaking, it's the same number. You don't need to go through and count. No one's going to count your work to make sure you have exactly the same number above and below. But that's a way to help you see if your line of best fit is correct, or if it's roughly speaking about the same. Okay? So this is about what we had before. And now we have a couple questions. So you can keep using the scatter plot you had. I think, well, mine was like that, something like that. So you keep using the scatter plot you had. And we have a couple questions about this. First off, so we graphed and we drew line of best fit, it asks to describe the type of correlation that is present in the data. So just like we were doing up above, what adjectives can we use to describe the relationship between the age of a car and the number of miles it drove? So we've got positive, negative, strong, weak, linear, or nonlinear, or no correlation. So let's start from the beginning. Would this line be positive or negative? Positive. It's positive because the line is going uphill from left to right. Okay, so it's positive. Would this be a strong or a weak? Let's see here. Well, most of this data is pretty tightly packed to this line. The only one that's not really is this guy up here. So I'm going to go ahead and say this is a pretty strong correlation. And then the last thing we have to talk about is it linear or nonlinear? Well, that's definitely linear. It's definitely a straight line. So this is a positive, strong, linear correlation. That is the type of relationship there is between these two variables, between the age and the number of miles. It's positive because as your age gets bigger, so does the number of miles. They both go up the same. It's strong because the older the car gets, the number of miles is being driven on it, and it fits pretty closely to this line. And it's linear because the points seem to follow a straight line. The second part here asks, what conclusions can you draw from the results of this study? So now it's asking us not necessarily about just like algebraically the data. It's asking us to draw a connection to the original problem. So problem was talking about a study comparing the age of cars and the number of miles it's driven. So is there a relationship between these two variables based off the data we were given that we plotted? Well, yes. There definitely is a relationship between them because of all of these adjectives we can describe to it. There's definitely a relationship. And what is the relationship? Well, as the age of the car gets older, the number of miles the car is driven increases. What conclusions can you draw from the study? I'm going to type it, I think. As the age of the car increases, the number of miles the car drives also increases. So that would be a conclusion we could draw from the data. That's something we can say is true based off of the data points we were given, the scatter plot we made, the line we drew, the adjectives that we described to it, all tell us that the older the car is, the more the number of miles it is driven. Letter B. The table below shows results from multiple surveys trying to find a link between years in school and time spent in jail. So we're going to graph the data in the space below, and this is actual data. It's not fictional. This is data that I found online in a survey, in a study. So you have the black on your paper. You do not have the blue, the percentages here. So what I'd like you to do is like you to take this data, and I'd like you to plot it in the space below. If you want to pause the video and do just that part, then afterwards we'll answer the couple questions that go with this. All right? So go ahead and plot the data. When you're ready to continue, hit play, and we'll go through it together. All right, so first thing we got to do is we need a scale. So whenever you're plotting, obviously, or not obviously, but in case you didn't know, whenever you're plotting data in a table, the first data value you get to is almost always going to be the X value, and the second one is going to be the Y value. Even if the data is given to a table, it's like left and right, then the first one is the X, the second one is the Y. All right. Maybe you didn't know that, but that is typically how a table will almost always be set up. So the years of school will be on the x-axis, and I have to go from 2 is my lowest, 16 is my highest. So if I've got 10 spaces, so this is years in school, let's see. Well, that's definitely going to be 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 won't work. But I bet if I count by 2, 0, 2, 4, 6, 8, 10, 12, 14, 16, that would be our highest data point. 18, 20, that's pretty good because we're using up most of the space. So let's do that. 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. All right. Now, our percentages. So this is probability of going to jail. I can't write this sideways. Going to jail. There. So probability of going to jail. So our lowest value, let's see, is 0.3. And the highest value is 1.5, 1.6. All right. So our scale has to go from 0, you always start at 0, and has to go up to about 1.6. And you might be thinking, oh man, this is really hard because now there's decimals in there. Ignore the decimals. Imagine that's the number 3 and that's the number 16 and 5 and 4 and 15 and 14 and 12 and 14. Use the same scale and then just throw the decimals back in there. So 0, I'm going to count by 2's again. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Now throw the decimals back in. 0.4, 0.8, 1.2, 1.6, 2.0. That scale matches our data nearly perfectly. Now, if you had trouble coming up with a scale and you were really lost up to this point, maybe you want to just copy what I have here, copy the scale, and then pause the video again and plot your data. If you choose to do so, I'd recommend it. Okay, let's see here. So, first point, we need 8 years, 1.4. 8 years of school, 1.4. 12 years of school, 0.6. 12 years of school. That'd be graduating. 0.6. 2 years of school. Ugh, person dropped out in 2nd grade. 1.6. 6 years of school. 6th grade. 1.5. 6 years. See, this is 1.4, so 1.5 would be here. 16 years. So that person graduated college. 0. Whoa, what happened? 16 years, 0.4. Alright, good. We're just on the bottom now. So 3, 3, and 1.5. 10, 1.2. 9 years of school. Oh, well, that's 10. Okay, 9 is here. 9, 1.4. 5, 5 is here. 1.5. 13, 0.5. So that's 6. 5 is here. And 15, 0.3. All right. So now we have this data plotted. So my first question to you, I know there's some other questions we're going to ask here in a second, but my first question is, just looking at this data, does there appear to be a relationship between the amount of time a person goes to school and their probability of going to jail at some point in their life. Yeah, I mean, look at this data. This data definitely has a pattern. It's not no correlation. There's not dots everywhere. So there does appear to be a relationship between the amount of time somebody spends in school and their probability of going to jail throughout their lifetime. I mean, this person who has, 16 years of school compared to the person who dropped out at second grade. This person who dropped out at second grade is going to be 4 times as likely to go to jail as this person who graduated college. Okay, so let's look at a couple questions we have that go along with this data now. And if you haven't answered these questions yet, actually it's just these two. So since it's still part of that same question, why don't you pause the video and answer these questions. So you have the data on your paper now. Answer these questions about it. So the first one's asking you to describe the correlation present. And the second one asking is, what conclusions can you draw from a result of the study? So go ahead and pause the video and answer these couple questions right now. And when you're ready to continue, hit play and we'll go through it together. Okay, so first things first is describe the correlation. So this data, let me see if I can switch colors to, we'll do red. No, green. So if I wrap this up in a burrito, that is, I would say, fairly linear. I mean, yeah, it has like this kind of hump here, this little bump where it goes up, but this is also only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 pieces of data, maybe 12 pieces of data. So I don't know if over time, if these couple are a little bit higher, but roughly speaking, I mean, look, it's fairly linear. So I'm going to go ahead and I'm going to say this is linear. Okay, so we'll say this is a linear correlation. And was it positive or was it negative? The line is going down, so this would be a negative. And before we switch page again, strong or weak? That's pretty strong. I mean, those points are pretty close to that line. So let's go ahead and say this is a negative, strong, linear correlation. So we're going to call this a negative, strong, linear correlation. And then what conclusions can you draw from the results of the study? Is there a relationship present between these two variables? The people who did this study and collected this data, what would they be able to say as a result of this study? Would they be able to say there's a relationship between the more time you spend in school, the less chance you're going to go to jail? Or are they going to say, well, the longer you go to school, the higher chance you go to jail? Maybe they found that there's no relationship between these two variables. They did a study and they found out there's no connection. What would they be able to say as a result of this study? So looking at the data, you could say there definitely is a relationship because it's the data seems to fit into a pattern. Linear, negative, strong correlation. So this appears to mean that the more you go to school, as your schooling increases, your probability of going to jail decreases. Look, a little bit of school, high chance of going to jail. A lot of school, low chance of going to jail. So the more schooling you get, the less chance, the less probability that you'll go to jail at some point in your life. So the more education you get, the less probability of going to jail. Oh, jail would be a conclusion of this study. So that would be something that would be true for this study. The more you go to school, the less chance you go to jail. We have letter C. It says Damien did a survey of 20 drivers that came into the DMV to renew their driver's license. Damien was interested to see if a person's age had any effect on how well they could read road signs. Use the data collected to construct a scatter plot. Draw the line of best fit for the data. Okay, so we need to construct a scatter plot and draw a line of best fit. So down below here we have this. So as before, the first variable is our x, the second variable is our y. So the driver's age, let's just call it age, in years goes here, and the sign legibility distance, that's how far away they can read the signs. So it is a good practice. It is always a good practice to label your axes. So age, sign, legibility, even if my writing is not legible anymore. And let's see, age. Well, we're talking about drivers, so you're not going to talk about anything less than 16. So we've got that is the lowest, and I'm looking for the highest. There's an 85 here, and that appears to be the highest. So my scale needs to go from at least 16 to at least 85. So let's see. 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. That would put 16 here and 85 here. That's pretty good. That's a pretty good scale. So I'm going to do that. 0. I'm not going to put... Whoa. I'm not going to write on every single line, though. 0, 10, 20, 30, 40, 50, 60, 70, 80. Whoa, what's that? That's 78. 80, 90, 100. Alright, and the sign legibility. Let's see. So the smallest legibility seems to be... There's a 350, there's a 250, 240. So we've got less than 240? Nope. So that's the smallest. And what's the largest? I see a 600. Anything bigger than 600? Nope. Alright, so we've got to go from 240 to 600. See, I guess we could go like counting by hundreds. I mean, we'd have 1, 2, like 100, 200, 300, 400, 500, 600. That put the highest here at 600 and the lowest here at 240. I wish there was something better though, because that's still a lot of wasted space up here and down here. 253, 354, 455, 556. Ooh, I like that. So I'm going to put a break in the scale. So I'm going to do ziggy-zaggy. So I'm breaking off everything in between here. I'm going to call this guy 200, 250, 300, 350, 400, 450, 500, 550, 600. So by putting this break in the scale, I got to kind of skip out some of the extra stuff I don't need, and it allowed me to space out my data a little bit farther here so I can make these connections possibly a little bit easier. So now we're going to go through and plot the data. And this could be some time-consuming, boring stuff because there's lots of pieces of data here. So feel free to plot the data on your own. Skip past this part of the video if you choose to do so. It's just going to be a lot of me flipping up and down plotting. So, sorry. Here we go. 16, 600, 16, 600, 55, 430, 55, 430. So you did that one and that one. 49, 400, 49, 400. 23, 500, 23 up to 500, 75 to 50, 75 to 50, 51 for 10, 51 400 for 10 would be like here, 22 580, 22 580, 35 for 10, 35 for 10, 85 400, 85 400, 67 to 40, 67 to 40. Okay, top row's done. Sweet. All right. So we've got 48 500, 18 540, 350, I'm sorry, 65 350, 65 350, 72 410, 72 410, 68 370, 430, I'm sorry, 35 430, 75 330, 75 330, 25 520, 25 520, 66 340, 66 340, 64 390, 64 390. All right, so we have all of the data plotted. Now, what it asks us to do? It asks us to graph the data, use a collected line to construct a scatter plot. Check. Draw a line of best fit for the data. All right, so I'm looking at this. It appears to be linear, going downhill. It appears to be going something along those lines. So a line of best fit for me, I'm going to use my line tool. You can use a ruler if you want to. Let's see. We draw it first. I might make adjustments to it in a second. Let's see if I like that. So I'm looking at it. I'm looking to see roughly if there's the same number of points above and below. Yeah, maybe a little this way here. I like that. I think the slope looks right. It seems to fit the data. I mean, if I had a 100-year-old, I'd expect their vision to be down here somewhere. And yeah, I mean, they seem to be following this line fairly closely. So I like that. I like my line of best fit I have there. Draw a line of best fit. Check. All right. And we got a couple questions here. So same couple questions. So first off, describe the type of correlation that is represented by the data, and then what conclusions can you draw? So what type of correlation is present? So we've got, is it strong or is it weak? I mean, that's an opinion question. I mean, you might think, oh, there's some wider outside here, so you might call this weaker. Fine. You might say, well, those dots are still pretty close, so it's strong. It's fine. I mean, there's no set definition of what makes something strong or weak in terms of just looking at a scatter plot like this. So that's kind of an opinion question. Me personally, looking at it, I'm going to say it's relatively strong. I mean, it's sort of strong. It's a little strong. I don't think it's weak. I don't think it's strong. I think it's someplace between the two. So I'm going to put relatively strong. Or sort of strong. A little strong. Strong-ish. Sort of strong. I mean, it's definitely not perfect. It's not, all the points aren't directly on the line. There's definitely going to be some variance out here. Like this guy has good eyesight. This person has terrible eyesight. And I mean, there are some that are further away from the line that are not right on the line. So if I would draw this burrito in here, it has this, I mean, it's going way far out in this range. Like these guys are all pretty good. I would call it strong up here, but it's kind of weak down here. That's why I'm kind of indecisive on how I want to describe it. Let's see. So we got strong or weak. We need, is it positive or negative? So is there a positive correlation or negative? The slope of the line we have drawn, the black line here, this is a negative line. So it's going downhill. So this is a negative correlation. And it was linear. So it's negative because as the person is getting older, their eyesight is becoming worse. There's the two variables aren't both going up or both going down. As one's going up, the other's going down. It's sort of strong, I said, because the gosh, why did I do that? Where am I? It's sort of strong because up here it's strong, down here it's weak, and so I said it's kind of someplace in between, and we saw why it's linear. So, what conclusions can you draw from a result of this survey? Can you say that there is a relationship between the age of a person and their ability to read road signs? So, based off this data, I would say absolutely. Because we have a fairly strong correlation, and the stronger the correlation, the more conclusive the results. If you had a really weak correlation, you could say, well, there's sort of a connection, but it's not really that good. Because we said this is fairly strong, or sort of strong, that means there's a sort of strong relationship between a person's age and their ability to read road signs, or the distance they can read road signs. So, what conclusions can you draw? Well, we can say the older a person gets, was it the farther distance or a shorter distance? It was shorter. Oh, I missed an R. The older a person gets, the how do I want to say this? The less distance they can read the road signs, the closer the road signs have to be, their vision is not as good. The older a person gets, the closer the signs have to be read. Closer the signs have to be read. I guess that works. I mean, you kind of get what I'm saying. So as they get older, the signs will need to be closer for them to read it. So they don't have such good vision distance as we get older, according to our data, according to our graph and our scatter plot. All right? Summary. So this is also a type 1 writing. 2 minutes. So type 1s, you just write. You write for 2 solid minutes. Don't stop. Do what it asks you to do. You get credit for it. So type 1 writing asks you, why do you think drawing a line of best fit would be useful when trying to make predictions based off a scatter plot? Because it's why do you think? That's an opinion. Your opinion can't be wrong as long as you put it down on the paper. So go ahead, pause the video, take your 2 minutes. When you're ready to continue, hit play, and we'll go through it together. All right, so again, why do you think it'd be helpful? I don't know. I mean, hopefully you said things like, well, I kind of made a prediction down here. I said, based off our line, if we were to continue and extend this data, I would expect, a 100-year-old would be able to see around maybe 200 feet. Now, you've got to be careful on how you're predicting, because if you go, well, this person who's 120 can see 0 feet. I mean, if a person lives to be 120 years old, they can see more than an inch in front of their face. So you've got to be careful on extending the data too far and extending your predictions too far. It's called extrapolating. You can't extrapolate too far past the given data because some things may start to fall apart. you might be able to make predictions. Let me erase some of this stuff up here. I can't erase all of it. Let me erase the blue. Delete, 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 delete. All right. So you might be able to say things like, well, even with your line of best fit, you might be able to make a prediction on how far a person who is 30. I mean, right there is where the line of best fit reaches 30. So you might be able to say, well, a person who's 30 years old typically needs about 500 feet of distance. They can read signs 500 feet away or closer. All right. Let's see other graphs. Make prediction. I mean, you can say the more. I mean, it'd be bad to say a person who gets 18 years of school has a 0% chance of going to jail, because trust me, there's people who go to school for a long time and they still go to jail. So you got to be careful about making extrapolating too far off the data, but you can still make predictions. I mean, I could predict how far this person who goes to school for 11 years, the chance of them going to jail is about a 0.8% chance. A car that is 10 years old might have 120,000 miles on it. That's not unreasonable. I've had cars that have had 120,000 miles on it. It's been 10 years old. Let's see what else we've got. Oh, that was the same data. That's no correlation. Volume, months pregnant. Yeah, so you can use these lines of best fit to help you make predictions based off of your data. It can be done, and I just showed you how. Okay, so this has been lesson 6.1. Thank you for watching.